with that. As you might imagine, I'll start from the ground because that seems like a sensible place to start. Depending on how fast you fire the thing, that's going to affect the motion, but also the angle from which you fire it is going to make a difference in terms of how long it's in the air for, but also how far the thing goes. So we talked about how firing it at a shallow angle means it hits the ground very quickly. Firing it at a steep angle means it hits the ground after quite a while, but still not very far from where you fire it. And if you want the sweet spot, you want to be somewhere in between the two. All right, so let's begin. Let's look at what happens when we start messing with the angle that something is fired from. And to keep things simple, to start with, we're going to look at this sort of scenario where we're dealing with a projectile fired from ground level. And I'm going to keep the initial speed at 10 meters per second for this one. But what I want to do is change the angle to something like 30 degrees. Partly because then horizontal and vertical motion will be a bit different. We won't have things cancelling that wouldn't normally cancel. But also because sine 30 and cos 30 are relatively nice numbers that we can work with, and sine 60, cos 60 similarly, because that'll be the same just the other way around. So this is the situation we're looking at. And we want to try to follow the same kind of procedure that we did previously. In fact, I'm going to zoom out a bit, change my gravity so I get something a bit more realistic. Go down to -1.6 and we're on the moon. You can see this thing travels a lot further on the moon. If we come down to -9.8, we've got projectiles on Earth once more. We'll stick with -9.8 for now. Feel free to throw different numbers into your calculations and see what effect it has when you change things. You might be surprised by the difference with the range if you modify a number like that just a little bit. Okay, so this is our scenario. We're going to see if we can reconstruct this horizontal range of 9.6 or close to it. Example, projectile motion from any angle and let's do this. A Nerf gun is fired with a speed of 10 meters per second from ground level on level ground. In other words, we're not firing it up onto a hill or up a slope or into a dip. It's basically from flat ground onto flat ground. The angle of elevation is 30 degrees above the horizontal. That phrase above the horizontal is technically redundant. The angle of elevation literally means the angle above the horizontal, but I'm going to include it here so that you've got some context. Elevation means lift it up. If you elevate something, you lift it up. So angle of elevation is how much you tilt the angle. When we were looking at this thingamabob, the angle of elevation at the moment, the lowest this thing goes is something like, I would say maybe 25 or 30 degrees, and it can go up to 45 up there. It's got it. I think it's got it marked on. It's got a 45 degrees marked on, all the way up to 90 degrees up at the top there. So yeah, I think we have 30, 40, 45, 50. There we go. So your angle of elevation you can change depending on what you want your projectile to do. It's not always the case that you automatically always go with 45 degrees. If you're trying to fire something over a wall, then you might need to prioritize height as opposed to horizontal range. Bear in mind, if you're firing a gun, if you've got a sniper rifle or something and you're firing at something that's half a mile away, you're going to need to take into account the fact that even though the bullet flies very, very fast sideways, it is still falling down at the same rate that everything else falls down. There's a classic conundrum that if you fire a gun and you drop a bullet at the same moment from the same height, which bullet hits the ground first? And the paradoxical nature of this is that actually they both hit the ground at the same moment, because if you fire the gun horizontally, the bullet is traveling much, much faster than if you drop a bullet, but not vertically. The majority of its velocity will be in the horizontal direction. It might be traveling horizontally at 200, 300 meters per second, depending on the gun, but it's only falling vertically at a speed of 0 at the beginning, and half a second later it lands on the ground. It's going to be barreling forwards still at a tremendous pace when it hits the ground, but it's going to be moving downwards at the same rate, and it's going to fall down in the same time it would take to drop, which is a bit of a strange one, a bit of a paradox. Now, I'm going to jump straight to the money question here. We're interested in the range. How far does the dart travel? But in order to get the answer to that question, we're still going to need to work through a similar process to what we did before. And I'm going to try to lay that out with bullet points. First, consider vertical motion to determine hang time. That's how long it's in the air for. Next, consider horizontal motion to determine horizontal range. And that's it. So we need both aspects, vertical and horizontal, but you'll notice that the hang time is the fundamental thing, the conduit between the two. By working out how long it takes, we can figure out how far it goes. We're also going to look at questions like, when does it get to its maximum height and what is its maximum height? But we'll start with this one because the horizontal range is a good starting point for a thing to calculate for a problem like this. And then we'll look at what happens when we mess with some of the values or try doing a slightly more algebraic version so that we can see the impact of things like changing the speed of your Nerf gun. How much more powerful does it need to be? I think back when my brother was a kid, he got into modifying his Nerf guns. So you take a regular dart and you maybe mess with the end of it so it becomes a little more dangerous because it's got a pin in the end, and you tweak the pneumatics inside it so you can fire the thing a bit more powerfully. We're going to look at how much faster you would need the thing to leave the gun in order to, say, double your range or quadruple your range. But we're going to begin with finding the horizontal range by first working out the time it takes. And this is usually how I lay things out. I'm going to do it all at once this time. We have a vertical motion on the left and a horizontal motion on the right. And I'd encourage you to do a similar thing with the way you lay out your work, because it helps you to see the two side by side, helps you to keep track, and the more clear structure you've got, the easier it is to work through a problem of this sort. So vertically, we have Suvat equations, and horizontally, we have speed equals distance over time. As I've said before, the most messy looking of the Suvat equations is typically the most useful. It's the one that links displacement to initial speed and acceleration and time, but it will typically come out as a quadratic. So we have S, U, V, A, and T. And on this side, we will have V, X, T. And crucially, the V here is not the same as the V over here. This V on the left is the final speed vertically, whereas the V on the right is the initial speed and the final speed and the average speed. It's the constant speed throughout the motion horizontally. So they're different things. And that's why even if you do follow my advice and put these two things next to each other, you're not going to have a complete table here, but I'd recommend you draw a line down the middle because it helps you to separate physically on your page between the V on the left and the V on the right. Now, the first few things we can fill in pretty easily. We can say the acceleration is equal to negative g because it's being pulled downwards by gravity. The next bit is s, and that's going to be 0. The reason that's 0 is that we're firing from ground level and it's landing at ground level. Although as it moves along, it will increase in height until it gets to its highest point, and then it will reduce in height once more as it goes along. by the time it gets to the end of motion, we're considering the entire motion of the thing from the moment it's fired to the moment it lands again at the same height. And the overall change in position, the overall displacement, is 0 meters. We can also fill in a couple of things on this side, potentially, but at the moment, you'll find that if we try to write down the initial speed vertically or horizontally, we have a little bit of a problem. Don't worry, it's not insurmountable, but it's a little trickier than what we had before. Previously, we looked at the initial speed and the thing was being kicked at a speed of 10 meters per second perfectly horizontally. So we just had a 0 for the vertical motion and we ended up with a 10 for horizontal. We don't have that anymore. If you fire this thing at an angle of 30 degrees, it's not traveling at 10 meters per second sideways, and it's not traveling at 10 meters per second vertically. It's traveling at some combination of those. It's not traveling sideways as quickly as it would be if you pointed it perfectly sideways, and it's not traveling vertically as quickly as it would be if you pointed it perfectly upwards. So we're going to need to break apart our vector a little bit to see exactly what's going on. For this, draw us a little picture. If we've got a vector, whether it's a force vector or a velocity vector, anything like that, we can use the fact that the angle tells us how much of the vector is pointing in any given direction. So I'm going to indicate on here the horizontal component with one arrow and the vertical component with a different arrow. And hopefully you remember some of this from the work you would have done with forces. It's the same with velocities. If we've got a velocity in a particular direction, like 10 meters per second, and we know the angle, in this case 30 degrees, we can make use of that to calculate for ourselves the horizontal and vertical components. This is just a right angle triangle. So you can either work it out the long way by putting a right angle in the bottom right corner and doing your SOHCAHTOA thing, or you can use the slightly more mechanics approach of saying, look, we know that if you resolve a force through an angle, you use cos, and if you resolve perpendicular to that direction, you use sine. So we get 10 cos 30 on the bottom and 10 sine 30 up the side. This is a common enough thing to do both in forces and in things like projectiles that it's a process you want to build familiarity with, get comfortable with this. So if this is our situation, we can fill in our vertical and horizontal motion velocities. The initial velocity vertically is 10 sine 30, which you can calculate gives you 5, sine 30 is a half, and then horizontally we've got 10 cos 30, which again you can chuck in a calculator and get an approximate value like 8.66, or you can get a more precise value, which is √3/2 times 10. So if you want to check that your numbers are sensible, it's not a bad idea to get the decimal approximation as well as an exact value. The exact values would be more useful for working through the problem without losing precision along the way, but an approximate value is good for a sense check. Think about the scenario. It's fired at 30 degrees. If you're firing something at 30 degrees, it's going faster sideways than it is vertically. It's closer to being horizontal than it is to being vertical motion, which means the component in the horizontal direction should be bigger than the component in the vertical direction. And that's what we've got, 8.66 horizontally and 5 vertically. So that's what we're expecting. And that's a very sensible place to do a quick verification for yourself in the middle of a question. Now, there's another interesting thing in here. We've got enough already. We've got S, we've got U, we've got A. That's 3 things. And therefore, we could use it to find T. That's the thing I said I was particularly interested in here. But incidentally, V is something that we could actually work out right from the beginning in this particular case. So I'll put a little extra note here. Because the motion is symmetrical when we fire from ground level to ground level, what can you say straight away about the final vertical velocity compared to the initial. I'll leave that as a question for you to ponder, see if you can figure it out for yourself. If you're not quite sure, then you could actually work it out using the Suvat equations and then say, well, why is it that? Now I can see what it is. Why is it that? And sort it through in your own head. But what we've got here is already enough. We're going to use S equals ut plus half at squared. And that will give me 0 equals 5t minus half g t squared. And that equation is something I can solve and find t. It's another quadratic. The last time we had a quadratic, it was just something t squared equals something. So we could rearrange and solve directly just by square rooting both sides. This one is a little more complicated, but not much more, because the last one was easy because it didn't have a t term. This one is easy because it doesn't have a constant term. We're lucky because we've started from horizontal ground and we're ending on horizontal ground. So although the initial speed is not 0, which would have made the t term disappear, the displacement vertically is 0. That makes the s term disappear. And that means that even though you could use the calculator again to solve this quadratic, you don't need to. All you need to do is pull out a factor of t, 5 minus g over 2t. And you've got a factorized quadratic straight away, no matter how awkward the numbers might be. And this gives us two solutions. Either t is 0 or the other bracket is 0. 5 minus g over 2t is 0, which would give you t equals 10 over g. You'll notice, I talked about this before, the fact that we've left it in as g means we can interpret this and say, what would it be like on the moon? And you can see that if you're on the moon, where the gravity is 6 times smaller, t would be 6 times larger. Things will stay in the air for 6 times longer than you would expect. So when you drop a feather on the moon, it's going to take 6 times longer to hit the ground than it would if you dropped it on the Earth. If you drop a feather on the Earth, it falls a meter during that time, it's going to accelerate. If you drop it so it falls for a second, for instance, it's going to fall 5 meters because the average speed during that first second is 5 meters per second, roughly, or 4.9, because it accelerates from 0 to 9.8 in 1 second. If you do the same thing on the moon, drop something from a height of 5 meters, instead of taking 1 second, it would take 6 seconds, because it's only accelerating at 1.6 meters per second per second. Now, we've seen this situation before. We've got two different values of t, and we need to select the one that's the one we want. And if you think about it, it makes perfect sense that there will be two values. We have asked this formula to tell us when is the nerf dart at ground level. And it's told us, quite accurately, twice. It's at ground level at the very beginning and after 10 over g seconds. Well, just because we already knew it was at ground level at the beginning doesn't mean the equation is not going to tell you it. But that one we can rule out, not because it's not true, but because it's trivial. If you say, when is this going to hit the ground? If I kick it from here, you say, well, it's already on the ground. Well, true, but not useful. So we're going to say after projection, first it returns to ground level at t equals 10 over g. Then just for completeness, we're going to do 10 divided by 9.81, should be just a little bigger than 1, and we'll give that answer to 3 significant figures, 1.02. That number is going to be important because, as I've said before, and I will say again, t is the conduit between vertical and horizontal motion. Is the crucial thing you need to link the two, because vertically the motion is not affected by the horizontal and vice versa. If the thing is in free fall, it's going to keep moving sideways at the same rate. But what we do know based on the vertical motion is how long it's in the air for, and as soon as we know that, we can come up here and fill in t. And here we found this by considering vertical motion first. Now we know both the horizontal velocity and the time it takes horizontally, we can work out the horizontal range. V equals x over t. That means that 5 root 3 equals x divided by, now what I'm going to do here is leave this as 10 over g, just because it will give me a more precise value. I will still round at the very end, but I don't want to use rounded values in the middle of a calculation. There's no point in rounding and then rounding again. I feel like a friend of mine at university who needed 50% to pass a course, and I think he was on 49.43%, but then the 49.47 maybe. So 49.47 should round to 49%, but they first rounded to 1 decimal place and it became 49.5, and then they rounded once more to the nearest percentage and it became 50%. If you start rounding and then rounding again, you're going to lose precision too quickly. I'm going to rearrange. We'll multiply by 10 over g. We get 5 root 3 times 10 over g, so 50 root 3 over g, and then we're going to put that into the calculator. So if I want 50 times root 3, and then multiply by 9.81, 850 to 3 significant figures. And the first thing I noticed there is that that answer doesn't make much sense. I've obviously done something wrong. It's almost certainly something to do with the calculation that I've carried out. In fact, if we look at this, common sense wise, we're saying that 8 and a bit x divided by approximately 1. So what's gone wrong there? If I multiply by 1, I should still get 8 and a bit. 850 is much too big. Because I worked out an answer and then multiplied it, I've missed whatever was on the calculator before. So I'm just going to type it in again and make sure I didn't type in 500 by mistake. 50 times the square root of 3. And then I need to multiply by 9.81. And now I see what I've done wrong. My answer is not just 10 times, it's 100 times bigger than it should be. It's because I've multiplied by 9.81 instead of dividing by 9.81. This sort of thing is a really easy mistake to make, but hopefully if you're thinking critically at every moment about whether your answer makes sense, it's an easy mistake to find as well. If I'd made a similar mistake down here with the time and done 10 times g, I'd be getting an answer of 100 seconds. And I think to myself, it's a Nerf gun dart. I fire it at 20 meters a second. That's not a crazy speed. You cycle at 20 meters per second. Sorry, 10 meters per second. That's 20 miles an hour. You can cycle at that speed. Nerf guns almost certainly are capable of that kind of speed. I think they can do 10 or 15 meters per second. It's not going to take it more than a minute for the dart to land. And by the same token, it's not going to travel nearly a kilometer. So we need to double check our numbers. 8.83 is a much more sensible answer. Make sure you're checking that your numbers make sense. They're just logical kinds of answers for the scenario you're dealing with. You don't need to be an expert. You don't need to know very much about rugby or lacrosse or whatever the scenario is that they might be describing, but you need to have a rough sense of what a sensible speed might be or a sensible time for something to be in the air. And the more questions like this that you do and that you consciously think about, deliberate practice where you're actively asking yourself and questioning the process as you go through, that will help you to build this sense of what numbers are sensible and where common mistakes might come in. Sometimes as daft as this, typing the wrong thing into the calculator twice in a row, and sometimes a little more insidious or subtle that you've got to go back through and hunt. For instance, this is positive because it's vertically upwards speed, but this is negative because it's acceleration in the downwards direction. All right, that was the range of my object. The next question is this: what is the maximum height reached of dart? For this, again, we'll keep going back to this. We look at vertical motion and we look at horizontal motion side by side. We consider each one in turn, and that's going to help us to work out what we're interested in. It might be that you don't necessarily need both, but let's say this question got augmented a bit. And how far horizontally from the point of projection does this take place? So Now it's got the maximum height, which is clearly vertical, but also the horizontal distance to that point, which is obviously to do with horizontal motion. Let's start with the vertical motion. And as we've done before, S, U, V, A, and T. We want to figure out which of these we know and which of them we need to calculate, which ones we can based on the formulae that we have. For starters, maximum height, that's what we're trying to find. We're looking for the vertical displacement between the moment when you fire the gun and the moment when it reaches its maximum height. So although previously we've considered the entire motion from the beginning of the firing the dart to the moment when it hits the ground, now we're just considering the first part from when it's fired to the moment it reaches its greatest height. We still can make use of what we worked out before. The initial speed is 5 vertically. We can, of course, always fill in the gravity minus g as the acceleration. But that's only two things. So unless you can figure out how long it takes or how fast the thing is going, we're not going to be able to work out the vertical displacement that we need. Well, there are a couple of things you might think about here. For a start, the time it takes is actually something that, although we've not worked it out directly, we've worked out something which we could use. The motion is symmetrical. Notice what I said here about symmetrical motion in order to help us figure out how fast the thing might be going at the end. Well, a similar thing applies here. You could say because the motion is symmetrical when we fire from ground level to ground level, what should the time taken be if the total journey time is 1.02 seconds? Possible to infer that directly because of the symmetry, but we're going to leave t for now and focus on v because it's more useful generally. If, for instance, I fire this from a height like the previous example, then it's not true to say that the halfway point is the highest point. In fact, with the previous example, if you remember, we were firing from firing horizontally. The highest point in this case is actually the moment when it gets kicked off the garage roof. And sometimes, even if you fire this with a slight angle upwards, the maximum will occur quite early on in the motion because it's got a long way to fall down afterwards. So in general, the more useful thing to do here is to set v equal to 0. Since at its maximum height, it is no longer moving upwards, but not yet moving downwards. You could think of it as the instant when the velocity changes from positive to negative. There's going to be a moment, and I say moment because it doesn't last any time, but when you throw something in the air, there is that brief snapshot when it's no longer moving upwards, but it's not yet moving downwards. And at that moment, the velocity is technically 0. It only happens for a single instant in time, but that's the point when it's at its maximum height, because it was moving upwards just a fraction of a second before that moment. So it was getting higher and higher all the way until that point. But as soon as that moment has passed, it starts moving downwards, so it's not going to get any higher again. This gives us enough things. We've got S that we need. We have U, V, and A that we know. And that's enough for us to work out what we want. So let's do it. S, U, V, and A, that's not going to be S equals UT plus half AT squared. It's not going to be V equals U plus AT. It's going to be the V squared equals U squared plus 2AS. Remember, there are effectively 5 formulae because there's a Suvat equation for every possible combination of S, U, V, A, and T. Any 4 of those you pick, like with this one, all except T. Or we could have everything except A, and that would give you the S equals U plus V over 2 times T, and so on. This one's the one that doesn't include T, and you can look them all up in the formula book. The only one that you might find that isn't in the formula book is this rather useless one, S equals VT minus a half AT squared, which is very similar to the one we often use, S equals UT plus half AT squared. If you ever happen to know the final velocity, but you don't know the initial velocity, you might find this one useful. But actually, often we just infer that one by making use of v equals u plus at to get a direct link between the two. In fact, substituting this one, v equals u plus at, into the other one to get rid of u is how you derive that other formula. Anyway, for this one, all we need is v squared equals u squared plus 2as. So 0 squared equals 5 squared plus 2a, so minus 2g times s. S is what we're interested in. In fact, you might even decide that you want to give this a variable name that's a bit more descriptive for the problem at hand. So we might call it h, and then we know that we're trying to work out the value of h. We can rearrange, solve, and we get h equals 25 over 2g. And then again, although I'm writing 25 over 2g so that I could use it later if I need a more precise value, I'm going to get an answer correct to 3 significant figures from the calculator, 1.27 meters. And then I'm going to do a quick sense check and ask myself if that seems reasonable. I'm firing a Nerf gun. It takes about a second. It travels 8 meters and 9 meters horizontally. Does it make sense that it goes about 1.27 meters up? Yeah, we're firing it at 30 degrees. It's not going to go up very far. It's going to go a lot further sideways than it is going to go vertically because most of its velocity is angled in the horizontal direction. It's going to travel sideways more quickly than it goes up and down. If the situation were reversed, if we decided to angle this at 60 degrees instead of 30 degrees, we'd have a very different picture. Let's see what happens. Reset all of this. We'll come back to that. GeoGebra is being a little slow. I talked about how far horizontally, and this is also something you could generate for yourself pretty quickly in this particular situation. If you think about the symmetry, you can probably guess if the overall horizontal range is 8.83 meters, and we can see the symmetry of this particular curve, you could probably guess how far along this point happens. But it's also perfectly doable to take information from the vertical and use it for horizontal. But to get between the two, we're going to need time. To find out anything horizontal, we'll need t. So we work out t as well. In fact, now we've got u, v, a, we need t. The easiest way is v equals u plus at, which gives us 0 equals 5 minus g times t. T equals 5 over g. You might recognize that. We had t equals 10 over g up here. It's an even more convincing way. If you've got an unsimplified version, you'll be able to convince yourself that it is exactly half. 10 over g, 5 over g. Horizontal motion, then we can say I'm interested in how far along it is. I already know things like, let's put v first. I know the horizontal motion starts with a speed of 5√3. It's going to have a speed of 5√3 throughout. We're interested in the horizontal range, and we know that t is 5 over g. So I'm going to substitute that into speed equals distance over time, and that's going to give me 5√3 divided by 5 over g. When I multiply both sides, I get 25√3 over g. You'll recognize that as well. When we worked out the total range, we got 50√3 over g. Now we're getting 25√3 over g. And if we do 5 times √3 divided by 9.81, 4.41, which is half of 8.82. There we go. That's how far horizontally the thing is going. Bonus question. How fast is it moving at the, or what is, how about this? What is the minimum speed of the Nerf dart during motion? Now, there's a couple of common misconceptions here. One of them is that the Nerf dart is traveling at 0 at one point. if you've ever been hit by a Nerf gun dart, particularly if, like me, you've recently been shot in the eye with one of these bad boys, you'll know it doesn't kill you, but it certainly doesn't feel like it's traveling at zero. What really happens is it comes in, it hits you, and then at the moment it hits you, it's traveling at whatever speed it was going just before it hit you, pretty much. And then it basically compresses a small amount. It has a very short space of time during which it decelerates to rest. So it is going at zero very, very shortly after it hits you. And it's that the force that your head exerts on the Nerf dart in order to decelerate it from whatever its speed is when it hits you to zero, which is the speed it's going at when it realizes it can't actually puncture your skull. If it decelerates rapidly enough, then you're going to experience that as a fairly large, if brief, force. So your head exerts a force on the Nerf gun exerts an equal and opposite direction force on your head, and that force is what decelerates the Nerf gun dart. If you're hit with something heavier, it might even knock you sideways, because the deceleration that the object experiences is not the only thing going on. You've got momentum involved as well, which is composed of the speed and the mass of the object. These are not particularly heavy, so it doesn't take a huge force to decelerate them, even if they're going quite quickly, especially if they're made of foam. But when they actually hit you, that's the point. When it first hits you, it's still in projectile motion. After it's hit you and it decelerates because it's touching you, that is no longer projectile motion, because weight is not the only force acting. So this thing is moving at speed. In fact, if anything, it's traveling at its fastest when it lands. And that would be the same speed it was going at when it took off. In this case, because it was fired from the same height that it lands at, it's going in a different direction when it lands. Instead of being pointing 30 degrees above the horizontal, by the time it lands, it's pointing 30 degrees below the horizontal. But it's still traveling as fast as it was before, because any vertical velocity it lost on the way up, it regained again on the way down. The moment when it's traveling slowest is when it's shed all of its vertical velocity and it's not yet picked it back up again. That is the same point that we've been discussing here. It's the point of maximum height. And we can see it here. We even use the fact that vertically it's traveling at zero when it gets to its maximum height. Therefore, the moment when it's traveling at its very slowest will be the moment when vertically it's not traveling at all. It's neither going up nor down. Horizontally, this never changes. It's like saying, when do you have the minimum amount of money in your bank when you've got two different accounts, and one is a savings account that's just got 30 quid and it always stays there, and the other one is changing. Well, you can ignore the one that's always staying the same and focus on the one that changes. You want to know when that money is at minimum, look at the one that changes and figure out when that one's at a minimum. So we just need to look at when the vertical motion is at its smallest possible value. And minimum speed is not just when is this at its smallest value, as in lowest value, but smallest value, as in closest to zero. We want to know when the vertical speed is zero. When the vertical speed is zero, the overall speed will be at a minimum. This occurs at the maximum point of motion. So you could say, and this is where I like to use vectors again, horizontally, we still got whatever speed we had at the beginning, 5√3. That was the 10 cos 30 that we had right at the start. And vertically, we've got a 0. If we want to find the speed at that point, we just work out the size of the velocity vector. This is simpler than it looks. I mean, you can work through it if you like, using Pythagoras, like we were talking about. You can have 5√3 squared plus nothing squared. And when you sort it all out, what do you get? Root 75, which, oh, surprise, surprise, 5√3. Most of this becomes effectively irrelevant, because what you're saying is, what's the size of this vector if it's traveling at 5√3 meters per second horizontally, and that's it? Well, obviously 5√3 meters per second. It doesn't have any vertical velocity, so the only velocity it has is horizontal. Sorry, Pythagoras, we don't need you for this one. We can do it all on our own. So there we go. This would probably be a good moment to stop and try a couple of questions in the book, depending on where you want to be, what you want to look at. You'll notice that the way the book works, they try to break this down a little bit further, I think, than perhaps they need to. There's an exercise at the beginning where we're projecting things horizontally. There's plenty of practice you can get with that. When we get to this bit, they talk about the u cos alpha and u sin alpha that we've been talking about here. They will often give you the initial velocity in vector form for some of these early questions as well, which you don't necessarily need as long as you're comfortable with using the angles. Typically, when you're given actual information for a real projectile motions problem, it'll be, well, here's the speed and here's the angle, and it's your job to figure out the I and J components, or the horizontal and vertical components. But if you're given something like an exercise 6b, where they give you perhaps particle projected with velocity which is already given in vector form, then basically you can read those off and say, aha, the horizontal speed is 4 at the beginning and therefore all the way through. The vertical speed initially is -5. That one will be an example where you're pointing down. So this whole exercise is really a way of sort of converting back and forth between the vector form and the speed and angle form. When we get to the next part from 6.3, you can see we're starting to work with scenarios a bit closer to what we were talking about. There's a bit of working backwards with some of these, and as I said, the next bit we're going to look at together is what happens when we generalize a little bit and we try putting in some constants like capital U for the initial speed and see how that plays out as we work through the problem. You can see some more examples in here, and then there's some questions in exercise 6C that you might recognize. So for instance, here's the speed of projection, here's the angle of elevation, how long does it take to reach its maximum height? Or it's projected from a point 5 meters above the ground, it's projected with this speed at this angle, how high is it 2 seconds after projection? In that particular case, you're not looking at the entire motion from beginning to end or the motion from beginning to maximum height, you're looking at a specific moment in time. So they give you the time, and from that you can work out both the vertical and the horizontal scenarios. You can figure out where it is vertically using SUVAT and where it is horizontally using speed equals distance